This Week in Science and Education is brought to you in part by the University of Western Ontario, www.uwo.ca. We thank them for their support. This Week in Science and Education is also brought to you by Laurentian University. Check out Laurentian at laurentian.ca. We thank them for their support.
Hey everybody, it's time for This Week in Science and Education. This is your host, Kevin Cougler. We are recording episode number 50 today. Diamond Anvil cells, recorded October the 6th, 2011. Hi everyone, thanks very much for taking the time to join us. We have a special guest today on the show. We're going to be talking with Linada Kaci today from the Department of Earth Science, Mineral Physics at University of Western Ontario. But before we get to our special guest, let's welcome in by video Colin Jagoe. Hi Colin.
How are you today? Hey Kev.
Doing well, doing well. And also on the line, but we can't see him today, is Dr. Thomas Merritt from Laurentian. Hey, Thomas.
Hello. Nice to be here, guys.
Good to see you, sort of.
Right.
Well, we've got a little technical difficulty. We're not sure what it is, but we'll have it sorted out for next week. In the meantime, Thomas will join us by audio. Let's get to our special guest today. Linada is going to talk to us today about diamond anvil cells. And I think we'll start the show off just by having you explain, Linada, what those are. And by the way, thanks for joining us. We appreciate your time today.
Thank you very much for inviting me. I'm very pleased being here and talk about diamond anvil cells and why they are used for and what type of research I'm doing. And it's very nice being here today. So let's go to the point. What a diamond anvil cell is. Well, it is a high pressure apparatus. It is used to generate high pressure. And in the heart of this apparatus, there are two diamonds. Two diamonds which are gem quality diamonds, the same diamonds that we see in rings that ladies wear. And but the difference is that the tip of these diamonds is cut. So these two diamonds has two flat surfaces. And the material that is being studied under high pressure, because these diamonds are, we know that diamonds are the strongest mineral in Earth, and that's the reason why we use this kind of material to generate high pressure. And they are used to make this, in these three recent decades, they have been developed a lot. And now, the recent studies, they can generate pressure up to 400 GPa, 400 gigapascal. And for those that doesn't know what this kind of measure is, I want to say that 1 gigapascal is 9,860 atmosphere, which 1 atmosphere is, and the idea of this kind of research is we cannot go in the deep of the earth. So what we want to do is we want to mimic what happened with these rocks and minerals inside our earth, and we generate this high pressure, and we know in this way all the properties of these minerals, like physical properties and crystalline structures, and how the atoms are arranged in their lattice, and how do they, this material can be even transposed, the transport, or have different phases. So yeah, it's pretty cool technique and very interesting. I'm very happy that I joined the Dr. Sean Shea group and working in the research, working with diamond anvil cells and working on making research of different kind of materials. And mainly I'm focused on studies of carbon dioxide. I am using the diamond anvil cell and studying carbon dioxide in high pressures. So what is important to say I don't know if I was clear. Hopefully, I was clear with the diamond anvil cells apparatus. This is the very main purpose of this apparatus. And if you have other questions, I can.
No, let me ask a quick question. So you've got the two diamond surfaces, and because the diamond is such a hard substance, you can get all that force between them. But how do you generate the force? What are you using to create that pressure?
So you saw there is the kind of an apparatus, and it is manually pressed. Manually, like there are screws that goes, like the diamonds are glue in some other stainless steel equipments. They are very small. They are not too big. They are as small as you can hold those in your hand. And and the let's say the material that is studied is very small. Is in the scale of micron. Is as big as the hair. Our hair is micro scale sample that is being studied.
Right.
Colin, how does this tie into to the curriculum? At what grade might students be learning about something like this?
Well, I'm just learning about it now, and I'm well past the grades. You know what? It's really interesting. I mean, there's all kinds of places where we learn about things, just like things like pressure and about formation of things in the earth and how, like rocks, for example, how rocks are formed and how they're modified inside the earth. And so there are places where this is sort of taught at a very basic level. I'm thinking. I want to get back to this cell. Like you mentioned that it was sort of manually controlled, and yeah, the two diamonds are really small, so they're sort of being pushed together. But I'm picturing in my mind like a big brake press or something that would just squeeze and squeeze and squeeze, and you get a big crank on it and squeeze these things down to get the desired pressure. Is that sort of how it actually works?
Yeah, it's a small apparatus. We use microscope in order to observe our samples.
Yes.
And of course, we use different kind of other minerals. We use, for example, ruby, which is a pressure standard in order that we can determine the pressure, how much is the pressure, or we use gold as a pressure standard too. Or we use pressure medium, so the whole environment where our sample might be has the same pressure. It is a very small chamber, like a microscale, but we all know that physical properties are the same in a microscale or in a microscale. What is physical? Like we are in micro, but we are still having lattice. A lot of atoms are there still, like. We are having a lot of stuff.
So one thing, just for clarification, you have an apparatus that's made out of diamonds, rubies, and gold. Is that correct?
Yeah.
I'm sort of curious where your lab is, and where the funding comes from. If I had flies made out of diamonds, rubies, and gold, I would be a very wealthy geneticist. So, one of the things. Sorry, Kevin was
expensive maybe, but yeah, it's a very interesting and useful technique and research.
It sounds awesome. So one of the things that Kevin was asking about is where we might run into this in education. And I'm trying to think when I would have talked about pressure way back in the dark ages when I was in school. And we used to teach phases. Just thinking of water and the fact that you've got water that can exist as a gas, a liquid, and a solid, and it depends on the pressure that's there, the temperature that's there. Are you doing similar kind of work? So you said you worked primarily on CO2. Did I have that correct?
Yeah. I'm working on carbon dioxide. Carbon dioxide is a gas, right?
Right.
In atmosphere is very is a greenhouse gas. So it's very known in global warming and all. Yeah, I'm working on carbon dioxide. It is, I don't know if you know that in high pressure and high temperature, carbon dioxide is a solid phase material.
Yes, and that's what I was going to get at. So are you working with so I mean, carbon dioxide when it's super cold, or when you work with dry ice. So
Yeah.
are you able to keep CO2 solid at higher temperatures by using high pressure? Is that the idea?
That is very cool, though. Like, how do I do that? I had the dry ice in a very small apparatus and inside of these two diamonds. Yeah, I can still carbon dioxide into these two diamonds. This was my major goal in this research. It was too hard at the very beginning.
Yeah.
And
okay,
it's too hard to have a good sample, because if you have a good sample, then you can really have good data after that.
That's fantastic. So apparently the key to the video this morning or this afternoon is simply you can't have both Colin and I at the same time. Okay, so Linada, in words that a high school student, so possibly even me, could understand, what have you found out about carbon dioxide by working with CO2 at such high pressure?
Okay, a lot of studies have been done by using this method and this technique about carbon dioxide, and mainly the studies has consist on phase diagram of this material in this kind of ranges of pressure and temperature, and it is like my research went a little bit more. I wanted to understand how this material is strong, like the strength of this material.
Yeah.
And there are altogether up to now discovered 7 different phases of carbon dioxide, 7 different crystalline forms.
Wow. Yeah. Okay. So explain what that means. What does a different phase mean to me or to a student?
Okay. So minerals has a crystalline form, and different minerals have different crystalline form. This is due to their chemical structure, chemical composition, but that might be even due to their physical properties like pressure and temperature. Mm-hmm. So in this case, carbon dioxide is the same chemical structure, but during too high pressure and high temperature, it undergoes to different kind of orienting. The molecule is oriented in a crystalline shape, different from different temperature and different pressure. It is different.
And what does that difference in crystalline structure mean to the CO2? Is it stronger or weaker?
That is the shape of a crystalline doesn't mean that it's stronger or weaker. The shape is a shape. It might be cubic, monoclinic. Like there are 7 major crystalline shapes: cubic, right, monoclinic, orthorhombic, crystalline shape. So different phase has different structure. Of course, that might imply how the distance between atoms and the bonds that are created are different.
Okay.
I don't know if I'm that clear for a high school student, but
no, for sure. I'm thinking it really has a lot of applications
it's a lot of crystallography involved inside. It's a lot of physics involved inside. But I want to make the point that what is interesting is that we can, using this kind of method and technique, we can mimic what is going on in the deep earth. So how do these minerals and rocks transform? Because they can even transform from one to the, because Earth is a moving object, even inside. We see plate tectonics moving in the surface, but it is a whole dynamic and thermodynamic inside the Earth happening. And these minerals, being strong or weak, that means that how they can flow inside the Earth easily or not that. So if carbon dioxide, for example, is a weak, it can flow easily more deep. So that implies people want to sequestrate carbon dioxide in the earth, but they don't know how deep can we sequestrate it.
Right.
And so this is a question I wanted to ask. So why CO2? So is CO2 naturally occurring in the Earth, or is this an idea that we're generating so much greenhouse gas, so much CO2, we need a repository? Is that what's driving your choice of CO2?
Well, I am interested even in planetary formation. If you know, carbon dioxide, as with other gases, is involved in the planetary formation. So, and of course, when the planets are formed, they are formed in a very high, extreme high pressure and temperature. So that is another interest on this study too.
Okay. So you've got this really interesting apparatus. You're working on CO2. Are there other researchers that are working on other substances using that same Anvil?
Yeah. In my lab, there are other lab mates that are working on different materials.
And so is there a common theme? What's tying all of this research together? Is it just that you have the apparatus to work on, or are you all interested in similar questions?
Pardon me, I didn't get that much the question.
Oh, I'm sorry. So what's the common theme across all these different projects with your different lab mates? Is it the high pressure? What's tying all of the research together?
Well, of course, we are using the same method and the same technique, and we, of course, face sometimes the same problems during the way. So we collaborate together and understand which is the better way to succeed and to have better results on using this.
Okay.
I don't know
this
if
is probably a good time to break for our commercial spots so we can thank our sponsors. And when we come back, we'll get Colin's perspective, and maybe he can do a little educational spin on this for us again. So let's take that time to have that break, and we'll come back in a quick minute.
This Week in Science and Education is brought to you by Sheridan Institute of Technology and Advanced Learning. At Sheridan, students shine brighter. Check out sheridanc.on.ca.
Okay, and we're back, and we're talking with our special guest today, which is Linada Kaci from the Department of Earth Science, Mineral Physics at University of Western Ontario. It's been quite an interesting discussion so far. I know Thomas is definitely getting a lot out of it, which is fantastic. Colin, what's your angle? What's your spin? What's your education, angle here for us?
The angle, you know what? There's all kinds of. It's fascinating to sit and to think in my mind where all the connections are with what we do here in secondary schools and high schools, because on the surface of it, you're studying earth science, which of course is a strand of what we study here as well. But then when you talk physics of crystalline structures and the chemistry of molecules and how they form, and then what that actually means in terms of a practical understanding of things like the inside of the earth, it's again one of these things that we've run across before on this podcast, and it's really an interdisciplinary idea that's drawing from all sorts of different areas from that basic foundation of science, but now you're using it in a way that you need all of these different bits and pieces. You didn't just study physics and go into this. You're looking at all of these different pieces. So my question, I guess, is if you were to talk to a high school science teacher or high school science student, what kind of things would you sort of recommend, or would you say to them if they're sort of keen in pursuing what you're doing? Because it's very interesting research. But what would you say to someone who's interested in looking at something like that?
Well, if that is very personal, I think everybody has its own interest in life, and but those who are very interested to know about minerals, about not only minerals but even material science, because this kind of tool are used in material science too. We are in the search of new materials, of strong materials, for being used in industry for different reasons. That might cover a huge range of different. I might mention. I don't know what to mention, because everybody knows that we are in the search of strong materials that can resist a lot of things. In this. I would like, I don't know, as I mentioned, it's personal. It's a matter of how you like and what you like to do. But those who are interested in finding new materials, this is the right study. Like, this is how we can create new materials that are not done before. Like, we can create diamonds by squeezing diamonds together.
That is so cool.
So,
well, I wonder if this is a good spot to wrap up today's show just by giving Thomas and Colin one more question each. Go ahead, Thomas.
So what's the next step? You've got this incredible instrument. Are you designing new instrumentation? Are you trying to ask new questions using the instrumentation you have?
The design of this instrumentation has been already done before. It has been evolved in these 30 years. That is how, due to the evolution of this kind of apparatus, we could reach from 100 GPa, and up to now there are 400 GPa, which exceeds even the center of the Earth, which is 360 GPa.
Okay, and that's a great point itself, and that should have been my question. So how does this force compare with the force of the Earth, and you're actually past the pressure within the center of the Earth?
Yeah.
That's fantastic. That's great. Thank you.
Yeah, thank you.
Colin, last point or last question today for our guest, and then we'll call it a show.
Sure. No. Just being exposed to this sort of field of study right now for really the first time, I want to know kind of what's the most interesting thing going on in the field, either things that are being discovered in your lab or interesting questions that people are trying to find the answers to right now. Like, what's the cutting edge in terms of questions people have in this high pressure, mineral studies in earth science?
Well, there are. I don't know if you want to know in my lab or if you want to know in general, because there is a whole society that is like researchers that are with this, and everybody has his own interest in a particular stuff. For example, for me, I was interested to know what is this carbon dioxide. My friend is working on sodium chloride and MgO, and phase D. Well, a lot of studies. Like, there are a lot of materials that you can study. That's the beauty, that you are not stuck in something. You have so many things to study, and using this, it's a good way. It's a very, very interesting and cool way.
Well, I think the only way that we can truly appreciate it is if you send Thomas and Colin and I some sample diamonds, and then we can kind of, really have an appreciation for it. Linada Kaci, it's been our pleasure to talk to you today on This Week in Science and Education. Thank you so much for taking the time to be here today.
Thank you very much. It was my pleasure to talking with you.
Yeah, thanks again for coming on.
There's another show on This Week in Science and Education. Thanks, everybody, for taking the time to tune in and be with us today, and we look forward to seeing you all again next week. Have a safe and happy week, everybody. Take care.